It's my great pleasure to present our today's speaker, Professor Andrei Lebedev from Belarus, and his talk is here on the screen. So thank you very much, Professor Lebedev, for agreeing to deliver a lecture at our seminar, and please go ahead. Thank you.
Thank you, the organizer, to invite me to join this active and excellent mathematical community. And my goal now is to show you, to present the goal of my talk is to show you that nowadays one can calculate all the roots of any polynomial with any prescribed accuracy. Once you have something like maple, so it will take you a few seconds, not more. So now to the talk. So I'm presenting the joint results of Mikhail Chernyatsky, Yuri Trubnikov, and myself, and they concern the the goal is the following. So first of all, let's recall the story of this method, the method I am going to tell you. So it's a rather long story, would say, that Daniel Bernoulli in 1724 announced the following result. Once we have a polynomial with real coefficients, then we can consider along with this polynomial the difference equation of the sort, so with the same coefficients. And once, say, this Tm minus n, Tm minus 1 are set, then you can calculate Tm and so on. And Daniel Bernoulli announced that the limit of this the solution to the solutions, or maybe terms of this equation turns to x0, where x0 is the largest in modular root of this polynomial. So Daniel Bernoulli didn't give a justification of this method. Later, 20 years later, Leonard Euler has written a book in Latin. It's something like this, not something. And in this book, chapter 17 is devoted, namely, to the justification of the new Bernoulli method. So, namely, what has done Euler? He considered so what we say now Taylor series or Lagrange series for this ratio 1 divided by p of x. P of x is this polynomial, and he proved that that under certain conditions, the corresponding limit, this is the limit of the terms of the correspondence of the Taylor series or Lagrange series, depending on when we just take the corresponding series at the origin or at infinity. And he also found out by examples, simply by examples, that sometimes beyond expectation that no root of the equation can be found through this method. So he found out by examples that not always this limit is equal to the largest polynomial, to the largest root of the polynomial. Then, in 1798, Lagrange considered the ratio of p prime divided by p of x, so derivative. So he considered it in order to eliminate the multiple roots. And again, he considered the corresponding Taylor series and Laureate series, and again proved the same formula. Of course, again, I'm going that not always we have the convergence here, but under certain assumptions. He said, if, for example, the assumption if there is only one in model. The breakthrough, in fact, in this direction was obtained by Aitken in 1927. What did Aitken do? He considered not simply these terms, but he considered a certain determinants built by means of these terms, and he proved Aitken again. All of them considered these polynomials with real coefficients, and in fact they considered only real roots of a polynomial, and Aitken proved that by considering the ratios not of the terms but of a certain determinants built by these terms, we can find not only this the largest or maybe the smallest in Model, but also some products of them. Again, he didn't. The main result of Aitken is when all the roots are different in modulus. So that's somehow the preliminary of this story. And Knani with Span in 2013, they have published a book, in fact, 2-volume monograph about thousands of pages. This is the whole monograph is devoted to the numerical methods for roots of polynomials. And namely, chapter 10 in this monograph is devoted to what I have mentioned before. And Jim McNamee, in his preface to the book, so he thanks his wife, and at the same time he telling us that he read hundreds of journal articles in preparation of this book, and this book covers the last few decades of the 20th and early 21st century, and he thinks that this book could be well entitled as a handbook of methods for polynomial root solving. So up to 2013, the situation, one can say, is described in this monograph. So now I'm going to add something to this monograph, and I will say that in fact there is a method, we will discuss it now, such that once you have something like Maple or some Mathematica or something like that, now we can calculate all the roots of any polynomial just in seconds. Of course, approximately, but with any prescribed accuracy. Okay. So let's go to the subject. Now, the objects. So we consider an arbitrary polynomial. Let Z1, Zp are its roots with multiplicities m1 and p, respectively. And let us consider the Taylor series for this fraction p prime divided by p. This is the Taylor series at the origin. I recall that the Hadamard determinant for this series, is the corresponding determinant that starts with ck and has r columns or r lines. That's it. And clear what is it. I also recall what is the Vandermonde determinant. The Vandermonde determinant is the following object. We said also that v of alpha 1 is equal to 1, and clearly this determinant is not 0 if and only if all these numbers are not equal to each other. So the first result links, namely the Hadamard and the Vandermonde determinant. Again, I'm recalling the Hadamard determinant for, so this is a polynomial, the Hadamard determinant is the corresponding determinant built by means of the terms of the Taylor series of this polynomial. So the first result is the following theorem that links Hadamard and Vandermonde determinant. Namely, this is a formula that relates Hadamard determinant Kr with Vandermonde determinant, and again the roots and multiplicity. In particular, we can see that there is the only term when r is equal to p, and namely this one term. And if r is greater than p, then this determinant is equal to 0 for all r greater than p. So in particular, we have from this result, we have that the ratio for p of hk divided by hk plus 1 is the product of all the roots of this polynomial. Again, I am saying what are they? These are the different roots of a polynomial we're considering it, and that's it. So that p are different roots, all the roots. So if you calculate this Hadamard determinant, and you calculate it by means of considering the Taylor series of this ratio, then once you found out that hkr is equal to 0, this simply means that we have strictly p different roots of a polynomial. That's it. And moreover, we can calculate the product of them by means of this formula. Okay, so this is the first result we are talking about. The second one result is in fact just by means of this ratio. We can not only calculate the product of this all the roots, but we can in fact calculate the product of any sequence of up to r, but under a certain condition. So this is quite similar to what Aitken has done. So the next result is the following. Once we are ordering the roots according to their models, the increase of the modeling. And once we have a situation when two roots are different in modulo, that R is less models, is less than that R plus 1, then the limit of the corresponding ratio, the same ratio, the limit of the corresponding ratio is equal to the product of these roots. And moreover, the convergence is here. The convergence has a geometric rate, so it's very fast. In fact, convergence, where this term U is simply equal to the ratio of these two roots. In fact, we can also estimate the constant here, but for practical needs, it's in fact not necessary, since the convergence is very fast, very good. So again, I'm showing the result. Once two roots are different in modeling, one can calculate the product of all the roots up to this one. Of course, with a prescribed accuracy, and I will show you by example. We can just estimate what is this Q. Okay. So first of all, note that that HK1 is simply CK, simply this coefficient, and therefore, for once we have the smallest root is a single one in modulus. The second one is greater. Then the corresponding limit. So this is namely the same limit, but here the limit of the terms, ratio of the terms of the Taylor series is equal to the first root, and of course the convergence is at a geometric rate here. Then the constant can be calculated, and in fact, in essence, this is the Euler's observation. So it was just Euler's observation. I recall it. I recall that Euler namely considered the Taylor series for the Taylor and Lagrange series for not this for the analogous, let us say, ratio, 1 divided by P of Z, and proved namely this formula. So Euler didn't give an estimation of approximations convergence rate. What is more important that in fact, this theorem is not only sufficient for conversion, but it is they are also necessary. Namely, we have the following result. Once we have two roots that are equal in modulus, then the corresponding limit is the same limit, but here we considered the situation when they are not equal in modulus. Then the limit does exist, and once they are equal in modulus, the limit there is no limit for this ratio. So in fact, we can, and we shall do this, we can observe when the roots are equal in modulus. That simply this limit should not exist. So, in fact, this theorem totally clarifies Euler's observation, and I recall that Euler's observation by examples, he observed that once a polynomial with real coefficients possesses two complex conjugated a pair of complex conjugated maximal and moduli roots, then the corresponding then there is no limit of there is no limit. In fact, the theorem tells us the corresponding roots, they do not need to be complex conjugated. They do not need to be complex. In fact, they can be even real. So one can consider the example of the following polynomial and consider the corresponding Taylor series, and of course there is no limit for this ratio. So this procedure I described a series of results that give us a possibility. We shall see that it really gives us a possibility to calculate the roots of a polynomial starting from the minimal one. Similarly, I will also now tell about the procedure such that we can calculate the roots of a polynomial starting from the maximal one in modulus. So again, let us consider a given polynomial and the corresponding now Lagrange series that at infinity. That means that the series we consider the modulus of that greater than maximum of moduli. And the corresponding Hadamard determinant now is again by the same formula defined, and we can. So we have here the analogous results as were before for the Taylor series. So first of all, the following theorem that we can link this Hadamard determinant with the corresponding Vandermonde determinants, and once this R is equal to P, so this is the only one summand here, only one term, so it is equal to this expression. And in particular, we have again the ratio of this hk plus 1 divided by hk is equal to the product of that1 up to that p. Okay, so we can always, first of all, once the corresponding determinant becomes 0, it simply shows us how many roots, different roots of a polynomial in question, and immediately we can calculate the products of all of them. And again, we can sequentially calculate the products of parts of these roots. So the analogy to theorem 2 is theorem 5. That once two roots are different in modulus, so say now we're calculating from the greatest one, the order is decreasing. And once two roots are different, we can calculate the product of these roots namely this product is equal to the limit of this ratio. And again, the rate of convergence, this limit sequence converges at a geometric rate. Okay, so where this Q is simply equal to the ratio of these two roots. Okay. So again, in particular, if this is R is equal to 1, so we have simply the corresponding determinant is simply bk. And this theorem turns out to be the following statement. Then once we have the greatest root is a single one in modulus. Then we can calculate it by means of this ratio. By means of this ratio, where the convergence is geometric. And again, I would like to mention that we have to consider, namely, this statement as a Euler's observation. Okay, that's it. And again, this result, this theorem not only a sufficient condition, but in fact it's also the necessary one, since we have the following result. Once if again we order the roots of a polynomial in decreasing order, and once there are two roots that are equal in modulus, then the corresponding limit doesn't exist. That again, once they're not equal, the limit does exist, and it is namely the product. Once they're equal in modulus, this limit doesn't exist. Okay. Now I would like maybe not to. I will, if we have time, I will comment on the proof of these results. But first of all, I would like to show you how they work to calculate all the roots of any polynomial. So first of all, let us remark something. First of all, there is no problem. Of course, there is no problem in finding multiplicities. Once we find a certain root, we simply calculate the corresponding derivatives and simply calculate the multiplicity by means of zeroing the derivative. Okay, this is one observation. So multiplicity are automatically calculated in this way. But in fact, we have something more. This result, this one, that there is no limit, is very useful, mainly for calculating these roots. How? And namely in this way. Once we see that there is no limit for this ratio or this ratio, in fact, there will not simply no limit. There will be always an oscillation effect. I'm not now commenting why. If I will have time, I will comment. So once we have a certain oscillation effect in calculating this sequence, then we simply understand, we see that we have at least two roots that are equal in modulus. So by means of changing the variable, we can always change the variable in such way that these roots will be not equal in moduli, and therefore we shall calculate it by means of the results when this limit and the corresponding limit will exist, and we shall calculate them. And namely how to change the corresponding the variable. We simply observe that if a complex number vector h is not a symmetry axis, it doesn't define the symmetry axis between these two roots, then if we shift the origin in this direction, this and implement the corresponding change of variable, then the corresponding roots of this new polynomial, they become not equal in modulus, and therefore they can be calculated by means of the given procedure. So, in fact, I'm again repeating. We can always somehow find out what roots are equal in modulus, simply considering these sequences and observing them as oscillating. And that's it. Then we change the variable. The symmetry axis between the roots, there are not, of course, there are not many roots of a polynomial. There are not many symmetry axes between the roots. So simply by saying trial and error method, we always quickly will find the necessary vector h, and therefore we will find the corresponding roots that are not equal in modulus. So let us present. Let us just present how the theorems that we're discussing how they work. So all what I am showing now has been implemented by Maple, and so Mikhail Chernявsky simply, this is nothing is done here by bare hands. Everything Maple does, so we simply say by telephone. And therefore, this is simply the example how it works. And all the tables, all the corresponding calculation is made by Maple. It takes, in fact, seconds, something like that. So, let us, by means of the results presented, let us calculate the roots of a polynomial. Of course, it is a model example. And we know its roots, this is this polynomial, but we will calculate the roots simply by means of this polynomial. We will not use the roots of polynomial to calculate. We will calculate them by means of the result presented. So, we exploit theorem 2. I'm recalling it now. So we calculate the roots starting from a minimal one in modulus. As I said, Wolfram Mathematica in seconds do the corresponding calculation. What do we have to calculate? We take a derivative and calculate the corresponding, not we, Wolfram Mathematica, calculate the corresponding Taylor series for this ratio and calculate the corresponding Hadamard determinants starting from. So here are the results. Again, nothing by hands. Everything is done by Mathematica. So we see the results, and we find out that the fifth one is equal to 0. So that means that we have 4 different roots, and their ratio, which is also calculated, is equal to 20i. That means the product of 4 different roots is 1. Now we can guess what is the rates of convergence of geometric convergence, but in fact it is not necessary. But of course we can guess. So there are 4 different roots that the ratio between them maybe quite possible that it is less than 0.9. So it's not important. But in fact, it's clear if we that since the convergence is geometric, so it's enough to consider, say, 50, 100 determinants with the corresponding that we have answer them. But it doesn't matter, 100, 200, doesn't matter for Mathematica. Then we took, namely for experiment, we took 150 steps. And I present simply the results for all the steps, both for the last 50 steps that are visible. So this is the step 105 and so on, 145. So here we are. So the product, this ratio is for 145 steps is this one. We see, and in fact, we took 25 decimal places in our calculation, but in fact doesn't matter. So it's clear that this is 0. So we have clearly I. So clearly, according to the theorem, so our first root is I, and calculating its multiplicity again by Wolfram Mathematica, we see that its multiplicity is 3. Okay. Now let's calculate the second root. To calculate the second root, we have to calculate the corresponding ratio of determinants. Again, by the same procedure, we have all zeros. So it's clearly the product, the product that 1 by that 2 is equal to minus 2i. So that means we have already the first one is I. So the second one is minus 2. Again, verifying multiplicity, everything by Wolfram Mathematica, nothing by bare hands. So we see that its multiplicity is 2. Again, starting to calculate it, the third root, after our ordering in modulus, we, again not with Mathematica, calculate the corresponding ratio, and what we see? We see that there is no convergence. The convergence should be very quick, very fast. But there is no fast convergence. Something, as I said, oscillation or something like that. But clearly no convergence. What does it mean? That simply means that there are at least two roots that are equal in modulus. So we have already, now we know that there are 4 roots, and we have already calculated 2 of them. So now it simply means that there are 2 roots left, and they are both equal in modulus. So what we have? We have to shift the origin in a way that it will not be the axis, symmetry axis between the two. We do not know what is the symmetry axis. So simply by trial and error, let's try. So let us say shift along the imaginary axis our origin. So again, this polynomial became this one. All this was from Mathematica again, I say. I'm saying again, take expansion into Taylor series, the same up to 150 terms, and what we have. Now it's clearly that it's converging. It's converging to this one. Clearly, we have this stabilization quite clearly. See, but somehow maybe a bit slow. Say converging. So one can stop at this moment, of course. But just for experiment. Let us implement a different shift. See, again, we already somehow guessed that this imaginary axis is not the axis of symmetry. So let us shift more. So let us implement a greater shift. And what we see then? Oh, now quite clear that we have perfect convergence, and that means that in this new variables we have the product which is equal the product of three roots, which is equal to this one, and returning to initial variables we calculate the initial root, which is 3 plus I. And finally, the last this fourth root can be calculated in this way. So the product is known, the through roots are known, the first one is also known. So as you see, we have, by means of the result presented, we have calculated the roots of the roots and the multiplicities of this polynomial. And in fact, one can see that it doesn't matter what we any polynomial, just take any polynomial and implement the corresponding procedure, knowing that the convergence is geometric and the lack of convergence means that there are roots that are equal in modulus. So here we are. Now I can comment a bit on the proof of the results. I recall that, in fact, there are, one would say, three main results. Let us see. So the first result is that we have the following formula linking the Hadamard determinant and the Vandermonde determinants. The second one is that the limit of the ratio of the corresponding Hadamard determinant is equal to this product once the roots are different in modulus. And the final one is once the roots, a pair of roots are equal in modulus, then there is no limit of this ratio. So let us comment on this three, the proof of these three results. So the first one. So the first one is just simply mean one has to calculate the determinant explicitly, and that's it. So if we take the expansion into the Taylor series of this ratio, then the corresponding terms here are equal to this one, and therefore we have to calculate the corresponding determinant. This is the Hadamard determinant. So simply using the properties of determinant, namely the one that determinant has proportional lines or columns and is equal to 0, we can calculate it, and we see that in the end we see that it is equal to what what it was written. Namely, this is somehow inverted Vandermonde determinant. So to make it Vandermonde, there will be some signs here that are not R but something else, and that's it. So in fact, the first result, this one is one can accurately calculate the determinant, and that's it. The second theorem. Now we have to calculate the ratio of determinants. These determinants. Again, if one takes the corresponding ratio, then we can write it in the following form, where this Q is equal to the ratio of these two products. And if this is not equal, of course, we only need the one is staying for this one. Of course, if this product is not equal to this one, then since that R is less than that R plus 1, here is standing something that is greater than that R, namely, it's feasible that, so this is Q. And here we have all the summands with the corresponding multipliers that are in moduli that are less than or equal to this Q. And therefore one see that we have the corresponding convergence. And in fact, we can even estimate the ratio of convergence. Not so difficult. Okay, so we have the second one. We have calculated or proved this result. Now, the most maybe peculiar result is that that we have no non-existence of the sequence once we have two roots that are equal. So again, if we consider the corresponding ratio, but now we consider it in a situation when that R and that R plus 1 are equal in modulus, but they are not equal, they only equal in modulus. Then this ratio, there are some multipliers with that are less, maybe there are multipliers only less than 1 or equal to 1, and no other multipliers are here. So we simply throw out all those one they do not influence the convergence, and what we have then. Therefore, we can consider instead of this sequence, the corresponding sequence where all the multipliers with QS are equal in modulus to 1. And there is at least one multiplier where this QS0 is not 1. So this is simply the multiplier that are divided by that R plus 1, but they are not equal to each other. Okay, so simply we have to find out that there is no convergence for this ratio. Okay, so what does it mean? So we are considering this ratio. We can consider all this QS as being written in this form. So they're just rotation. At this moment, we consider them as rotations. And there can be two situations. One is when all these Cs are rationally commensurable with 2 pi. that means that this ratio is irrational. Once they're rationally commensurable, that simply means that this sequence is periodic with the corresponding period, with the least common multiplier. Okay, so this is periodic, and of course it has no limit. It's not a constant, because it's not a constant. Okay, so the first situation. The second situation is that some of them are rationally incommensurable with 2 pi. Then that means that this ratio is irrational. So then we divide all these summands into those that are rationally commensurable, and these ones are rationally incommensurable with 2 pi. These are periodic, as we know, so we consider instead of this sequence a subsequence. We take the corresponding period, and they are now constants. And all of them, these ones are rationally, these multipliers are rationally incommensurable. Well, but what does it mean? That means that we can consider these numbers, these numbers, as simply the numbers that are situated on m-dimensional torus, e power I ts. This is q d, and the closure of all the sequence of this trajectory, say, is a submanifold of the torus. Namely, what submanifold? It is submanifold of dimension greater than 1, where m prime is a number of rationally independent numbers here. So, anyway, the trajectory is a certain submanifold on the torus. That means that the trajectory is this, say, this sequence simply something that goes on the torus. It is not periodic, but it is what I said, oscillating in a way, but not equally. It is not constant. It is not convergent in any way. So here we are, in fact. So that's it. Okay. Finished.
Okay, well, thank you very much for a very nice presentation. And we have time for questions, if any. Well, may I have, meanwhile, one short question? What about power of polynomial? What if the power will be increasing?
What does it mean increasing?
I mean, what about big powers?
Any fixed polynomial. It's not increasing. Yeah.
But
Sorry,
I'm saying
what
that
does it mean? What does it mean increasing power?
Yeah, I'm saying that you take a concrete example with a fixed power, right?
No.
With a fixed degree, I'm sorry.
This is an example, Alexey.
Yes, yes, but for instance,
to show
my idea, yes, my idea is as follows. Assume that you have polynomials which are partial sums of a certain holomorphic function. For every such a polynomial, you can calculate or you can estimate zeros, right?
Yeah.
Then if you take the degree of the partial sum to infinity, can you track the zeros? Can you estimate how the behavior? What I mean?
Alexey, this is a new problem.
Yes, I understand.
At the moment, I don't know. Okay.
Yeah, that's what came to my head, because you know the issue of zeros of algebraic functions is quite serious issue, no? And if
Yeah,
you
I
have a
think
powerful,
so yes, that's what mainly I not had in mind, but somehow some problems of this sort, I'm sure that they can be now attacked by means of this observation. Since
yeah, but you have to understand, or you have to somehow.
certain Hadamard determinants, you have certain estimates, so you have one can do something, but not me at the moment.
Yeah, but you have to be sure that your method is stable when you just take a degree of polynomial to infinity.
No. Sorry, no. For for a given polynomial, we consider the Hadamard determinant. And this k is this is not the power of a polynomial. This
Yeah,
is
understand. Yes, it's
this
approximation
simply,
parameter, right?
this is the terms of this Taylor theorem.
Yes, I understand, but
that what is going to infinity? The terms of this Taylor theorem. That's it.
yeah.
And nowadays, what is
Okay.
really, one can say, funny. Nowadays, something like Mapu calculates this sort of Taylor series just seconds, no problem. For a given polynomial, again saying. So, but I understand, and I'm absolutely sure that by means of this idea, we can obtain some new result in rational approximation and something like that. But it's simply somehow it simply somehow tells us, let's consider not only this ratio but just any rational function. Just tells us you have to consider Miroslav functions, and simply so. But it was not the thing. Oh my God!
Yeah, but still, it's not clear for me how you'll handle the growth of degree when you need to be sure about some stability of your calculations. But okay, as you said, it's another problem. It's a big problem, I guess. Okay, well, maybe more questions. No, I don't see any hand. But the presentation was clear, I guess, for everyone, and it was very nice. Thank you. And let's then thank speaker for very nice presentation.
Very
Thank you
interesting.
very much.
Thank you.
Thank you.
Thank you, Professor Lebedev. It's our pleasure to have you at our seminar.